Well, I'm not fully back from my hiatus. The hiatus is still continuing, so don't get too excited, regular subscribers. But I am going to have a little break in the hiatus, and again, your wishes for speedy resolution of some of the issues I've been working on are greatly appreciated. We're going to discuss just some basic aspects of special relativity. I am not equal to the task of standing in Einstein's shoes. We're not going to get into general relativity or even into some of the issues of, let's say, mass increase as an object travels close to the speed of light. We're going to talk about length contraction and time dilation, basic special relativity. We have let's just sort of jump into it now. We have a rocket ship, and the purpose of our exercise today is to prove that relative to our frame of reference, which we're going to call stationary, on board our rocket ship traveling near the speed of light, the length contracts, meaning 5 inches, meaning 5 feet might become 5 inches, but also the time will contract, meaning 5 hours to us might become 5 minutes. And we're going to discuss why that is. Now, first of all, I told you we're not going to really get into it in depth. There's a reason why it is that the obvious question is, well, the rocket ship is traveling at a certain percent the speed of light, but aren't we traveling at that percent the speed of light going back the other way? I mean, it is relativity, right? Relativistic, frames of reference. Why not? Why doesn't the time dilation go the other way? And the answer would be acceleration. Okay, the rocket ship is accelerating with respect to our frame of reference, which becomes stationary based simply on the fact that there's not energy being expended accelerating us. Okay, so that gets into some complicated issues. That gets into general relativity and the equivalence of gravitation and acceleration. But it also means that some of the formulas we're going to be exploring today aren't 100% precise because they don't take into account acceleration. So we're going to be discussing V pertaining to the rocket ship, but it's not going to be 100% accurate because it's not going to take into account the acceleration getting us to V, unfortunately. So, and there's not much that can really be helped with that at this point, simply because the video that we're doing here is going to be essentially elementary. We're going to be discussing a rocket ship traveling at, well, let's stick with this picture for now. Okay, make it simple. We're going to be discussing a rocket ship traveling at a certain velocity with a light beam bouncing back and forth at velocity c. Okay, so the light ship's traveling at v, and then the light is bouncing back and forth at velocity c. We are observing that light beam traveling on the direction of this hypotenuse. Okay, because again, let's say the light starts here and it moves up here. It will start here and then will move along here. Okay, according to our frame of reference. Now, is light really a photon traveling at the speed of light c? Looking at it from the standpoint of quantum mechanics, that gets a little more complicated. Einstein believed in the particle nature of light, and the light is a photon traveling at a constant speed. It's a little more complicated than that when you get into quantum mechanics, but we're just going to kind of stick with the basics here. So, anyways, it would seem from logic that if light is traveling at speed c and the rocket ship is going at speed v, then from our standpoint, this light traveling along this hypotenuse would be traveling at faster than speed c, right? The square root of v squared plus c squared, to be precise. Seems simple. Kind of like if we have a train traveling at a velocity and a guy jumping up and down. Let's say a guy jumps up. The train, if we were to look at the top of his head, it would seem to be traveling faster than the train. In fact, it would be traveling at the square root of the velocity of the train squared plus his velocity jumping up squared, the square root of the whole thing. Okay, the square root of vt squared plus v, the dude squared, the square root of that whole thing. Okay, so, but that's not the case according to Einstein. Oh, and Lorentz. Okay, Lorentz and Einstein. Einstein's given the credit because he was the one with the actual intuition that light is a constant velocity, that light is constant from every frame of reference. So, in a sense, the theory of relativity is a theory of non-relativity when it comes to the speed of light. It might almost be misnamed in a way. Okay, at least special relativity. So light is traveling at the same velocity relative to us that the alien or the human on board the rocket ship sees a light traveling. In other words, the alien on the rocket ship sees light traveling velocity c. We're going to see light traveling velocity c. Now, there's only one way that could possibly be. And the only way that could possibly be, if light is traveling at velocity c, but over a longer distance, then that means that longer distance can't be a longer distance anymore. I mean, think about it. Okay, that longer distance has to contract. In other words, space and time is now no longer absolute. Light is the absolute, not space and time. So light is traveling at velocity c. We are going to see light go from here to here in a time t that is relative to us. But if this is longer than, let's say light travels 186,000 miles per second, okay? But let's say that this entire length is longer than 186,000 miles, and yet light's going to travel in 1 second. Well, guess what? That's got to mean it's got to contract to 186,000 miles. It's actually a little more than 186, but 200 and something. But you get my point, okay? In other words, the length is going to have to contract. Now, this is a monumental insight, okay? The length is going to contract such that, let's go back here, it makes it easier. The length is going to contract such that this hypotenuse is now this length. Okay, this hypotenuse crunches into being this length relative to us, okay? Well, there's a lot of funny business here, and I am the first to admit I didn't draw this all that well, but I have a length c in time t, okay? But that distance here is now going to crunch into this distance here that we see with the rocket ship, with the light bouncing up and down, which is actually, if this is ct and this is vt, then that's going to be the square root of c squared minus v squared t, okay? So that's going to be, so c sub t is going to become this length. So c sub t is going to become the square root of c squared minus v squared t due to length contraction. Now, what is our factor for length contraction? Well, it's going to be our c squared minus v squared, the square root of c squared minus v squared, or this, all over c t, okay? Let me rephrase that. The square root of c squared minus v squared of t all over c of t. Well, the t's are going to cancel because it doesn't matter what t is. The ratio is going to be the same. And all over c, if we were to bring the c into the radical, it would be all over c squared. So it would be the square root of c squared minus v squared over c squared inside the radical. And that reduces to the square root of 1 minus v squared over c squared. So our length, as we view this hypotenuse, let's say, if it were at rest, would be L sub O. Okay, but our new length is going to be L sub O times the square root of 1 minus v squared over c squared. How am I doing for time? We better speed it up a little bit. So the length is going to contract by exactly this factor here, square root of 1 minus v squared over c squared. As we go towards the speed of light, which we never reach, but let's say we did, it would actually contract to 0, okay, because v would become 0, and the square root of 1 minus v squared over c squared would be 0. Another interesting thing to note, okay, and the interesting thing to note is as space contracts, so does time, okay? So our L over T, from the perspective of the rocket ship, is going to be equal to L sub O over T sub O, which is going to be equal to C. Well, why? Because C is constant. So our light beam is going to be constant as it travels distance L and also distance L sub O. So that means not only does length contract, but time contracts also in order to keep a perfect ratio here. Well, as we follow the algebra, that's going to mean that if we cross multiply, that's going to mean that L times T sub O is going to be equal to L sub O times T. And that's going to mean that L, if we take L and substitute L sub O times the square root of 1 minus v squared over c squared in for L, that's going to mean that L sub O times the square root of 1 minus v squared over t squared times t sub O is equal to L sub O times t. And if we cancel the L sub O on both sides, that gets us our formula for time dilation right here. Thank you very much.